There exists an object class that refuses the familiar story. It behaves as a cosmic monster, not in the sense of mythology, but in the sense of measurement. It violates the expectations that are usually reliable when mass becomes extreme. It is not a black hole. It is something that can be smaller than a city while outweighing the sun, something that can rotate so rapidly that timekeeping must concede it, something whose gravity is intense enough to sculpt matter into shapes that should not remain coherent, something whose magnetic field can become so strong that empty space is forced into new rules. It is the most compact, stable form of ordinary matter known to exist, and the adjective stable is not a comfort here, only a statement that it persists. It is a neutron star, and within that category, there are individuals that strain even the neutron star story, objects whose observed behavior pushes repeatedly against limits that were once treated as firm. A cosmic monster that breaks every rule, and it is not a black hole, is not a paradox for effect. It is the central fact that a certain set of compact stars can be both more extreme than almost anything else in the cosmos, and yet still possess a surface, still have structure, still be describable as matter rather than horizon, still emit signals that carry information from their exterior, still interact with their surroundings in ways a black hole cannot. The rule breaking begins with the most basic quantity, density, not as a poetic word, but as mass divided by volume. The simplest ratio that becomes violent when the numerator becomes astronomical and the denominator becomes small. A star is, in ordinary circumstances, an equilibrium. Gravity attempts to pull inward, pressure attempts to push outward. The star's existence is the compromise between those two tendencies, maintained through a chain of physical processes that convert microscopic interactions into macroscopic support. In a main sequence star, that support arises from thermal pressure produced by nuclear fusion in the core. Fusion heats the plasma. Heated plasma exerts pressure. Pressure resists compression, and the star stands. When the fuel changes, the balance changes. When fusion can no longer provide sufficient outward pressure, gravity becomes less opposed, and the star begins to contract. That contraction raises temperature and density, sometimes igniting new fusion stages, sometimes not, depending on the initial mass. The story that ends in a neutron star is the story of a core that has become too massive to be supported by electron degeneracy pressure, but not so massive that it must inevitably collapse into a black hole. The phrase electron degeneracy pressure is often treated as a technical flourish, but it is a first principles consequence of quantum mechanics. Electrons are fermions. Fermions obey the Pauli exclusion principle. No two identical fermions can occupy the same quantum state simultaneously. In a dense object, available quantum states in position and momentum space become crowded. To compress further, electrons must be forced into higher momentum states. Higher momentum means higher kinetic energy, and that kinetic energy manifests as a pressure that resists compression even at zero temperature. This is not thermal pressure. It does not come from heat. It is a pressure born from the structure of quantum state space. In a white dwarf, that electron degeneracy pressure can hold up the star's mass against gravity up to a limit. That limit arises because at sufficiently high densities electrons become relativistic, and relativistic degeneracy pressure responds differently to compression. The relationship between pressure and density changes such that beyond a certain mass, no equilibrium configuration exists for a cold electron-degenerate object. That mass is on the order of a solar mass, and in the real universe details shift it slightly, but the concept is firm. There's a boundary where electron degeneracy fails to provide a stable outcome. When a stellar core exceeds that supportable mass, it collapses further. As the collapse proceeds, electrons are forced into protons through inverse beta decay, a weak interaction process. A proton and an electron combine to produce a neutron and a neutrino. The neutrinos, weakly interacting, escape or diffuse depending on the density and timescale, carrying away energy and lepton number. The core becomes neutron-rich. Now the pressure that resists further collapse is no longer dominated by electrons. It becomes dominated by neutrons, which are also fermions and therefore also exhibit degeneracy pressure. But the rule breaking is already underway because the neutrons are no longer isolated in the gentle sense of a laboratory neutron. They are packed in a regime where nuclear forces, the strong interaction, become essential. The object is supported by a combination of neutron degeneracy pressure and the repulsive components of the nuclear force at short distances. The equilibrium that results is a neutron star, a core that has collapsed until matter reaches densities comparable to atomic nuclei, where the average separation between nucleons is on the order of a femtometer, where the concept of discrete atoms has ended, and where the solidness of matter is not the electromagnetic stiffness of electron clouds, but the stiffness of nuclear matter itself. The first rule a neutron star breaks is the rule of scale, the intuition that extreme mass implies large size. A neutron star can have a mass around 1 to 2 times that of the Sun, concentrated into a radius of about 10 to 15 kilometers. This is not a guess, not an aesthetic. It is consistent with observations of neutron star masses in binary systems and with constraints on radii derived from X-ray timing, thermal emission modeling, and gravitational wave signals from mergers. Even without citing specific datasets, the reasoning remains first principles. For a given mass, the smaller the radius, the stronger the gravitational field at the surface. The surface gravity of a typical neutron star is about 100 billion times that of Earth. That number is not a flourish. It is the direct consequence of Newtonian gravity's scaling modified by relativistic corrections. If Earth's surface gravity is G equals gm/r superscript 2, then compressing a solar mass into a radius of 10 km yields a g that is enormous. But Newton's formula is not sufficient because the star is compact enough that general relativity becomes essential. The compactness parameter, roughly gm/rc superscript 2, is not negligible. For a neutron star, it can be around 0.1 to 0.2. That means that the gravitational potential is a significant fraction of c superscript 2. In such a regime, time dilation and gravitational redshift are strong. Photons climbing out from the surface lose energy. Clocks near the surface tick more slowly than clocks far away. This is not speculative. It is the meaning of the metric around a compact object. And yet, unlike a black hole, the neutron star has a surface. There exists a last layer of matter that is not merely a mathematical boundary, but a physical one, where infalling material strikes and releases energy, where radiation can emerge, where magnetic field lines are anchored, where crust fractures can occur. The existence of a surface is a fundamental rule difference between neutron stars and black holes, and it is also a reason neutron stars can behave in ways that feel more violent. Energy can be stored in the structure and released catastrophically. The second rule broken is the rule that matter at such density should behave simply. In a neutron star, matter is not a uniform ball of neutrons. The name is a convenience, not a full description. A neutron star has layers, and the physics changes with depth in ways that are not optional details, but required by equilibrium. Start at the outside. There is an atmosphere, often only centimeters thick, composed of plasma whose composition depends on the star's history. Hydrogen and helium if accreted from a companion, heavier elements if processed in thermonuclear bursts, or possibly exotic compositions if magnetic fields are enormous. Beneath that atmosphere lies the outer crust, a lattice of nuclei embedded in a degenerate electron gas. As depth increases, pressure increases, and electron capture occurs, driving nuclei to become more neutron-rich. At greater depths, neutrons begin to drip out of nuclei because it becomes energetically favorable for neutrons to exist free rather than bound, given the extreme neutron chemical potential. This region is the inner crust, a lattice of neutron-rich nuclei immersed in a sea of superfluid neutrons and degenerate electrons. The idea of a superfluid is not ornamental. At temperatures relevant to neutron star interiors after they cool below a critical temperature, neutrons can form Cooper pairs, analogous to electrons in a superconductor, leading to superfluid behavior. Superfluidity implies quantized vortices in rotating systems, which becomes important for pulsar glitches, abrupt changes in rotation rate. Even the crust is not a simple solid. It is a quantum solid in a sea of quantum fluids, and the coupling between crust and superfluid interior can store angular momentum and release it in discrete events. Deeper still, in the outer core, nuclei dissolve entirely, and matter becomes a fluid of mostly neutrons with some protons, electrons, and possibly muons to maintain charge neutrality and beta equilibrium. The protons, though the minority, can also become superconducting, meaning magnetic flux can be quantized into flux tubes. The interaction of neutron vortices and proton flux tubes becomes a dynamic system capable of explaining observed timing irregularities, relaxation behaviors, and the long-term evolution of magnetic fields. Then the inner core, which is the real seat of the monster's refusal to obey familiar rules, becomes a domain where the equation of state is uncertain. The equation of state is the relationship between pressure, density, and temperature. For a cold neutron star, temperature is often a secondary variable after early cooling, and pressure as a function of density becomes the central unknown. At densities several times nuclear saturation density, new degrees of freedom may appear. Hyperons containing strange quarks, meson condensates, deconfined quark matter, or color superconducting phases. Each possibility changes the stiffness of the equation of state, which in turn changes the mass-radius relation and the maximum mass. The monster breaks rules because the microphysics is forced into a regime where the standard hierarchy of forces reorganizes. Electromagnetism that dominates chemistry becomes less important in setting bulk properties. The strong force, which is usually confined to nuclei, becomes the architect of macroscopic stability. Gravity, which is usually weak compared to other forces on small scales, becomes strong enough that the bulk object structure is determined by space-time curvature, not merely by Newtonian attraction. The third rule broken is the rule of rotation. Neutron stars can rotate extraordinarily fast. Conservation of angular momentum explains why. When a rotating core collapses to a smaller radius, its moment of inertia decreases, so its rotation rate increases. But the rule breaking is in the magnitude and in the stability. Millisecond pulsars rotate hundreds of times per second. Some rotate over 700 times per second. The equatorial velocity can be a significant fraction of the speed of light. At such rates, the star is not spherical. It is oblate, with an equatorial bulge. The balance includes centrifugal forces, and in relativity, frame dragging becomes relevant. A rotating mass drags spacetime around with it. In the Kerr metric for rotating black holes, frame dragging is dramatic near the horizon. But neutron stars also drag spacetime in a measurable way, affecting orbital precession and signal timing in binary systems. The rotation also interacts with the superfluid interior. In a superfluid, rotation is carried by quantized vortices. The number density of vortices is proportional to the angular velocity. As the star spins down due to electromagnetic torque, vortices must move outward and annihilate to reduce the superfluid's angular momentum. But vortices can pin to the crust lattice or to flux tubes, creating differential rotation between crust and superfluid. When pinned vortices suddenly unpin and move, angular momentum is transferred to the crust, producing a glitch. The key is that a glitch is not merely a timing anomaly. It is a manifestation of quantum mechanical coherence on a macroscopic astrophysical scale. The star's rotation is governed, in part, by the quantization conditions of a superfluid. That is a broken rule relative to everyday matter. The rotational behavior of an object with the mass of a star can show evidence of quantized flow. The fourth rule broken is the rule of magnetism. Many neutron stars have magnetic fields in the range of 10 to the power of 8 to 10 to the power of 12 Gauss. Some, called magnetars, have fields up to 10 to the power of 14 to 10 to the power of 15 Gauss. For comparison, Earth's magnetic field is about half a Gauss. Laboratory magnets reach tens of thousands of Gauss. A magnetar's field is so strong that it alters the structure of atoms. In such a field, the cyclotron energy of electrons becomes large compared to atomic binding energies. Electrons are forced into Landau levels. The spatial distribution of electron wave functions becomes elongated along field lines. Atomic orbitals become cylindrical. Chemical behavior changes. The vacuum itself, according to quantum electrodynamics, becomes birefringent. The polarization of light propagating through the magnetized vacuum can split, as the virtual electron-positron pairs that constitute vacuum polarization respond to the field. In that regime, empty space is no longer optically isotropic. The monster's field makes a medium out of vacuum. That is not metaphor. It is the QED correction to Maxwell's equations in strong fields, captured by the Heisenberg-Euler effect of Lagrangian. The consequences appear in the polarization signatures of X-ray emission and in the propagation of radiation near the star. The magnetic field also stores energy. The energy density of a magnetic field is B superscript 2/8 pi in CGS units. 4B10 to the power of 15 Gauss. This energy density is enormous. And integrated over the volume where the field is strong, the stored energy can rival or exceed the energy released in many astrophysical explosions. Magnetars release this energy through crust fractures and magnetic reconnection, producing giant flares that emit intense gamma rays and X-rays. Unlike black holes, which have no material surface to fracture, magnetars can store stress in a crust and release it suddenly. The rule breaking here is the coupling between gravity, nuclear matter rigidity, and magnetic field energy, creating a system where the magnetic field is not merely a feature, but a primary reservoir of power. The fifth rule broken is the rule of luminosity and radiative behavior under accretion. In a binary system, a neutron star can accrete matter from a companion. Infalling matter releases gravitational potential energy. For a neutron star, the potential well is deep, so the energy per unit mass released can be a significant fraction of rest mass energy. The efficiency can be around 10 to 20%, depending on radius and spin, compared to about 0.7% for fusion in stars. That means that accretion onto a neutron star can be a more efficient engine than nuclear fusion. It can produce X-ray luminosities that, if sustained, can reach or exceed the Eddington limit for spherical accretion. The Eddington limit is derived from balancing radiation pressure against gravity for ionized hydrogen. When luminosity is high, photons scatter off electrons, pushing outward. If that force exceeds gravity, infall is halted. But neutron stars can exceed this limit in certain conditions because geometry matters. Magnetic fields channel accretion onto poles, reducing the effective cross-section, and because the scattering opacity changes in strong magnetic fields. In magnetized accretion columns, radiation can escape sideways, and the effective Eddington limit can be higher. This allows ultraluminous X-ray pulsars, neutron stars that emit above what would be expected for their mass if emission were isotropic and opacity were classical. Such objects appear to break the Eddington rule. The deeper principle is that the Eddington limit is not a universal ceiling. It is a derived constraint with assumptions. The monster does not violate physics. It violates the assumptions humans tend to forget they made. The presence of pulsed emission, tied to rotation, confirms the accretor is a neutron star rather than a black hole, because pulsations imply a rotating magnetic field modulating emission from hotspots on a surface. Now the core of the mystery, the part that most directly matches the idea of a cosmic monster that breaks every rule and is not a black hole, is the boundary between stability and collapse. There is a maximum mass a neutron star can have. Beyond that, no pressure from nuclear matter, no degeneracy, no repulsive force at short range can halt gravity. The star collapses into a black hole. The value of that maximum mass depends on the equation of state. Observations of massive neutron stars, around 2 solar masses, set a lower bound on the maximum. Any proposed equation of state that becomes too soft at high density, such as by introducing particles that reduce pressure at a given density, may fail to support such masses. At the same time, observations of radii and tidal deformability constrain the stiffness. The monster lives in this tension. A neutron star near the maximum mass is a marginal object, a configuration where a small change in mass or internal composition could trigger collapse. But unlike a black hole, which is defined by an event horizon that hides the interior, a neutron star near maximum mass can still have an observable exterior, can still emit thermal radiation, can still pulse, can still experience starquakes, can still merge and produce gravitational waves with tidal effects that encode information about the interior. The existence of a surface and the absence of a horizon means the monster is interrogable in principle. That is the reason it is scientifically profound. It is the densest stable matter accessible to observation, a laboratory for strong gravity and strong interactions that does not immediately erase its own information behind a horizon. To see why a neutron star is not simply almost a black hole, it is necessary to revisit what a black hole is at the level of space-time. A black hole is not defined by density. It is defined by causal structure. An event horizon is a boundary such that events inside cannot influence the outside. It is a global feature of space-time. A neutron star can have comparable compactness but remains outside the horizon condition. The Schwarzschild radius for a non-rotating mass m is Rs equals 2gm/c superscript 2. If an object's radius is less than Rs, it must be a black hole in classical general relativity. Neutron stars have radii greater than their Schwarzschild radii, but not by a huge factor. For a two-solar mass object, Rs is about 6 kilometers. If the radius is 12 kilometers, the ratio R/Rs is 2. That is close in the sense that the gravitational field is strong, but it is far in the causal sense. Signals can escape. The gravitational redshift might be significant, but it is finite. A photon emitted from the surface will be redshifted by a factor related to the metric component, roughly 1/2 gm/RC superscript 2, 1/2 for a non-rotating star. For a compact neutron star, this might reduce photon energy by tens of %, but the photon still arrives. For a horizon, the redshift diverges. The monster's closeness to a horizon makes it a regime where relativistic effects are prominent while still allowing emission. That is the rule-breaking compromise, almost horizon gravity with pre-horizon observability. The monster also breaks the rule that an object's shape should be smooth. Neutron stars can carry deformations, mountains, though the term mountain is misleading because the height might be millimeters or centimeters. But with such intense gravity, even small deformations correspond to significant quadrupole moments because the mass is huge. A rotating deformed neutron star emits gravitational waves. The amplitude depends on ellipticity, rotation frequency, and distance. The concept matters because it ties mechanical imperfections in nuclear matter to space-time radiation. The crust, though thin, can support shear stress. The maximum sustainable ellipticity depends on crust composition and thickness, on whether the core is coupled, on the strength of the lattice. In magnetars, the magnetic field itself can deform a star. Internal toroidal fields can create prolate shapes. Poloidal fields can produce oblate deformations. The star becomes a gravitational wave antenna powered by its own imperfections. Black holes can emit gravitational waves through dynamics like mergers and ring-downs, but an isolated black hole in vacuum cannot support a persistent time-varying quadrupole moment because it has no material structure. A neutron star can. That again is the surface and structure difference, a fundamental rule difference. To stay within the topic, the object remains a neutron star, but the specific cosmic monster, referred to by the premise, is best captured by the most extreme neutron stars, magnetars and near-maximal mass pulsars, and ultraluminous X-ray pulsars, all of which share the same underlying theme. A compact star that exhibits behaviors that, if only the luminosity or energy scale were seen without context, might be misattributed to a black hole. Yet the observational signatures prove otherwise. The monster breaks rules of emission stability, of magnetic field strength, of rotation, of matter rigidity, and of the apparent ceilings derived from simpler assumptions. It does so while remaining an object with a definable surface, with a crust, with modes of oscillation, with glitches, with bursts, with a magnetosphere that can co-rotate and then slip, with plasma that can become charge-starved, with accelerating gaps that produce curvature radiation and pair cascades. Begin at the magnetosphere. A rotating magnetized neutron star induces an electric field. In the simplest picture, a perfectly conducting star rotating with angular velocity omega and magnetic field B produces an electric field E, omega times R, times B/C. This electric field can rip charges from the surface or accelerate charges in the magnetosphere. The magnetosphere is not empty. It becomes filled with plasma that can screen the electric field parallel to B, enforcing a condition of co-rotation out to the light cylinder, the radius where co-rotation speed equals c, given by r_l equals c/omega. Beyond the light cylinder, field lines cannot co-rotate rigidly. They open. The configuration becomes a rotating, magnetized plasma system that launches pointing flux and particles, extracting rotational energy and causing spin-down. Pulsar emission arises from coherent radio processes and high-energy emission from particle acceleration. The details of coherent radio emission remain complex, but the principles are anchored. Charges accelerated along curved magnetic field lines emit curvature radiation. Gamma rays can produce electron-positron pairs in strong fields via one-photon pair production or photon-photon collisions. Pair cascades supply plasma. Gaps form where charge density deviates from the Goldrake-Julian density required for co-rotation. The magnetosphere is a circuit. The star is a generator. The load is space. That is a rule-breaking object because it turns rotation into electromagnetic beams with clock-like regularity. But the monster aspect appears when these systems become unstable, when the field becomes so strong or twisted that it can no longer remain in a low-energy configuration, when the crust yields, when a magnetosphere undergoes reconnection events that dump energy in milliseconds, when the observed luminosity can outshine the entire galaxy's background in high-energy bands for a brief time. The interplay between crust and magnetosphere is central. The crust anchors magnetic footpoints. If the internal field evolves, perhaps through Hall drift in the crust or ambipolar diffusion in the core, stresses build. The crust, though strong, has a yield strain. When it fractures, it can shift the boundary conditions on the external field, twisting it further, leading to reconnection and energy release. The flare is then not purely magnetospheric and not purely crustal. It is a coupled instability. That is a rule-breaking mechanism relative to black holes, which lack such anchored fields and crustal stresses. The monster also breaks the rule of thermal behavior. A neutron star is born hot, around 10 to the power of 11 K, but cools rapidly by neutrino emission. Neutrinos dominate cooling for the first 10 to the power of 5 years or so, depending on processes. In the core, neutrino emission can occur through modified Urca processes or, if proton fraction is high enough, through direct Urca processes, which are much more efficient. Pairing gaps from superfluidity suppress some neutrino processes but introduce others, like pair breaking and formation neutrino emission near the critical temperature. The cooling curve depends on the interior composition and superfluid properties. Observations of surface temperatures and ages can constrain these properties. Again, the monster is not merely hot or cold. It is a macroscopic object whose thermal evolution is governed by weak interactions and quantum pairing in nuclear matter. Heat transport in the crust depends on electron conduction, and in strong magnetic fields conduction becomes anisotropic. Heat flows more readily along field lines than across them. This creates surface temperature anisotropies, hot spots, and pulse thermal emission. The star's surface can show patterns that are not simply due to accretion, but due to magnetically channeled heat flow. The monster is therefore an object where thermal maps encode magnetic geometry, and magnetic geometry encodes internal stresses, and internal stresses encode the evolution of matter phases deep within. Return to the equation of state, because every rule broken by the monster ultimately traces back to how pressure responds to compression at supernuclear density. If pressure rises quickly with density, the matter is stiff, and the star can support larger masses with larger radii. If pressure rises slowly, the matter is soft, and the star is more compact with smaller maximum mass. But the presence of a surface and the ability to oscillate and deform make it possible to probe that stiffness through tidal deformability in mergers. When two neutron stars orbit each other, their gravitational fields raise tides. A stiffer star deforms less. This affects the orbital evolution and gravitational wave phase. In a late in-spiral, the waveform carries imprints of the tidal love numbers, dimensionless measures of deformability. From these, constraints on radii and the equation of state can be extracted. The monster's interior, otherwise inaccessible, influences the motion of space-time itself in a measurable way. Black hole binaries also produce gravitational waves, but their tidal deformability is essentially zero in classical general relativity because black holes do not have material surfaces that develop tides in the same sense. Thus, the presence of tidal effects is another rule difference. The monster is matter, not horizon, and matter resists deformation. But the most dramatic rule breaking in the not a black hole sense comes from events where matter impacts a surface. In an accreting neutron star, material falls and forms an accretion disk if angular momentum is present. In the inner disk, gas heats to X-ray temperatures. In black hole accretion, the inner boundary condition can be the innermost stable circular orbit, and material can plunge through the horizon without a surface impact. In neutron star accretion, material must eventually strike the star, unless halted by magnetic pressure at the magnetospheric radius. The impact forms boundary layers or accretion columns, producing emission that can include thermonuclear bursts. Type 1 X-ray bursts occur when accreted hydrogen and helium on the surface undergo runaway nuclear burning. The surface acts as a pressure cooker. Degenerate conditions can make burning unstable. The burst rises quickly and decays as the layer cools. In some cases, deeper carbon burning can produce superbursts lasting hours. These phenomena require a surface, require accumulated fuel, require ignition conditions. They cannot occur on a black hole. Thus, a neutron star can look like an engine as luminous as a black hole system, but then it reveals itself through bursts and pulsations. That is the breaks every rule feeling, luminosity regimes, and variability timescales that rival black hole accretors, yet with signatures that only a surface-bearing compact star can produce. A further rule is broken by the existence of quasi-periodic oscillations and neutron star seismology. The star can vibrate. The crust can support torsional shear modes. The core fluid can support various oscillation modes, including F modes, P modes, G modes, R modes. These modes couple to the magnetosphere and can modulate emission during flares. Some magnetar, giant flares, have shown quasi-periodic oscillations in their tails, interpreted as seismic vibrations. If correct, these oscillations provide constraints on crust thickness, shear modulus, magnetic field configuration, and coupling between crust and core. The object becomes a resonant body, like a bell, but the bell is 10 kilometers across, weighs more than the sun, and rings in X-rays. The rule broken is that a star can be treated as an elastic object in certain respects, not just a fluid sphere. Black holes can ring too, in gravitational waves, through quasi-normal modes of spacetime, but that ringing is entirely different in origin. Neutron star ringing includes material shear. Again, structure matters. Then there is the rule of composition. The neutron star's crust contains nuclei arranged in a lattice. As density increases, these nuclei change. In the deepest crust, competition between nuclear attraction and Coulomb repulsion can produce nuclear pasta phases, rods, slabs, and other complex geometries that minimize energy. These phases are not decorative. They affect transport properties, neutrino opacity, viscosity, and the coupling between crust and core. They also affect the star's ability to sustain deformations, which in turn affects gravitational wave emission. The monster's matter is not merely dense. It is geometrically complex on microscopic scales, and that microscopic complexity influences macroscopic observables. The rule broken is the naive expectation that extreme compression yields simplicity. Here it yields new complexity, emergent structures forced by competing interactions. At the boundary between crust and core, the pressure and density conditions determine where nuclei dissolve. The transition affects the crust thickness, which affects the star's moment of inertia distribution. Pulsar glitches constrain how much superfluid is in the crust and how strongly it couples. If the crust is too thin, it cannot store enough angular momentum in pinned vortices to account for large glitches. This has led to the realization that core superfluid must participate, or that entrainment effects modify effective masses. The monster thus forces revisions of microphysical parameters based on macroscopic timing. The star is a lever. Small-scale physics becomes testable because the object magnifies it through its extreme conditions. Another rule is broken in the realm of spin evolution. A neutron star spins down through electromagnetic torque, but in accreting systems it can spin up, recycling old neutron stars into millisecond pulsars. The equilibrium spin can be set by the balance between accretion torque and magnetic torque. The fastest spin rates observed constrain the star's radius and equation of state. Because at too fast a spin, the star would shed mass at the equator, reaching the mass-shedding limit. The Keplerian frequency at the equator depends on mass and radius and relativistic corrections. Thus, observed spin rates constrain compactness. A very stiff equation of state might allow larger radii, lowering mass-shedding frequency, potentially conflicting with observed fast spins, though details depend on mass and rotational deformation. The monster's rotation becomes a constraint on nuclear matter stiffness, again connecting macroscopic to microscopic. In the context of cosmic monster that breaks every rule, the most striking individual category may be magnetars because they combine extreme fields with violent transient behavior while still being neutron stars. A magnetar's field energy can dominate over its rotational energy, unlike typical radio pulsars where rotation powers emission. The magnetar's persistent X-ray luminosity can exceed its spin-down power, indicating another energy source, magnetic dissipation. That breaks the rule that pulsar luminosity is powered by spin-down. The magnetar's bursts and flares can release energy far beyond what rotation could supply over the timescale of the flare. That breaks the rule that steady reservoirs must be tapped slowly. But the reservoir is magnetic stress and internal field energy, and the release can be rapid because reconnection and crust failure can proceed on Alfvén timescales, which in these environments can be milliseconds to seconds. The magnetar also breaks the rule that magnetic fields are passive. Here the magnetic field shapes the star's surface emission, alters vacuum propagation, deforms the star, and dictates thermal conductivity. Yet another rule is broken in the phenomenon of fast radio bursts when magnetars are implicated as sources for at least some events. Within the scope of the topic, the key is not to drift into broad FRB astrophysics, but to recognize that a neutron star with magnetar strength fields can produce coherent radio emission of extraordinary brightness temperature. Coherent emission implies phase-related charge motion, which can arise from plasma instabilities in magnetospheres. The brightness temperatures inferred require coherence, because incoherent emission would violate energy constraints. The magnetar environment provides conditions for strong electric fields and pair cascades. The monster, thus, can generate signals that look impossible under ordinary radiative processes. But the rule being broken is again a rule derived under ordinary conditions. Under magnetar magnetospheres, the plasma parameters are extreme and the coherence constraints can be met through collective behavior. The object remains not a black hole, and yet can produce brief bursts that can be detected across cosmological distances. Return again to first principles, because the rule breaking must remain grounded. Gravity compresses matter. Compression raises density. At high density, quantum statistics sets pressure even without heat. At higher density, nuclear forces contribute, and the composition adjusts through weak interactions to minimize energy. The equilibrium is described by solving the Tolman-Oppenheimer-Fokoff equations, the relativistic equations of hydrostatic equilibrium. They relate the pressure gradient to the enclosed mass energy and the metric. Unlike Newtonian hydrostatic equilibrium, in the TOV equations, pressure itself contributes to gravity, because in general relativity, not only energy density, but pressure gravitates. This is another rule broken relative to everyday intuition. Pressure is not merely support. It is also a source of gravitational field. In a neutron star, pressure is enormous, so its contribution to the gravitational mass energy is non-negligible. This tightens the feedback. More pressure supports against gravity, but also increases gravity. The balance becomes delicate. This is why maximum mass exists. In Newtonian gravity, one might imagine arbitrarily stiff matter could support arbitrarily large masses. In general relativity, the gravitational role of pressure and the causal constraint that the speed of sound cannot exceed c limit the stiffness. Therefore, even with the strongest possible equation of state consistent with causality, there's an upper bound to neutron star mass. Observations of neutron star masses near two solar masses already force the equation of state to be sufficiently stiff, but not infinitely. The monster lives in that narrow corridor of possibilities. A black hole is simpler in some ways because, in classical general relativity, the no-hair theorem suggests that an isolated black hole can be characterized by mass, spin, and charge, with charge usually negligible astrophysically. A neutron star is more complex because its multipole moments depend on internal structure. Its magnetic field can be complex, its surface composition can vary, and it can carry memory of formation and accretion history. This complexity is not decorative. It is the reason the object can break rules repeatedly. Different internal compositions and field configurations can produce different external behaviors, making neutron stars a diverse population of monsters, all within the same category of compact stars. Consider the boundary condition of a surface in strong gravity. A photon emitted from the surface must climb out of a deep potential well. The energy loss is gravitational redshift. The observed temperature of thermal emission is thus lower than the local surface temperature by the redshift factor. The apparent radius inferred from flux and temperature is also affected. Observers define a radiation radius, R infinity equals r/QRT, 1, 2 gm/ RC superscript 2, for a non-rotating star, which is larger than the physical radius. These relations mean that observations must be interpreted relativistically. Furthermore, light bending is strong. Photons emitted at an angle can be bent and still reach a distant observer, making more than half the star's surface visible at once. In extreme compactness, nearly the entire surface can be visible due to light bending. This affects pulse profiles. Pulse shape modeling can constrain compactness. The monster's gravity thus alters the geometry of visibility, smoothing pulses and allowing hotspots on the far side to contribute. In black holes, light bending also occurs, but without a surface hotspot that emits thermal radiation in the same way. In neutron stars, the interplay between surface emission, rotation, and light bending produces rich observables. Now focus on the idea of breaks every rule as an internal narrative driven purely by the topic. The object breaks the rule of what a star is. A star is usually a luminous sphere sustained by fusion. A neutron star is a star's remnant that may shine by cooling, by accretion, by magnetic dissipation, by rotational energy loss, but not by core fusion. It breaks the rule of material states. Matter is neither gas, nor liquid, nor solid in the usual sense. Parts are lattice, parts are superfluid, parts may be superconducting, parts may be exotic. It breaks the rule of timekeeping. Rotational periods can be stable to extraordinary precision, rivaling atomic clocks in fractional stability over long timescales, yet interrupted by glitches that are abrupt and quantized in effect. It breaks the rule of magnetism. Fields become so strong that the vacuum becomes a medium. It breaks the rule of emission limits. Accretion-powered pulsars can exceed naive Eddington assumptions. Magnetars can produce flares powered by magnetic reservoirs. It breaks the rule of observational access to strong gravity. It provides a surface to emit signals from a regime close to a horizon. Each broken rule is not a violation of physics, but a reminder that the regime is beyond ordinary assumptions. And the monster is not a black hole, because it is an object where matter still participates, still resists, still fractures, still supports waves, still holds magnetic field lines, still creates a magnetosphere anchored to a rotating conductor. The deeper the examination goes, the more the monster becomes a set of coupled differential equations across scales. Microscopic interactions define an equation of state. The equation of state defines the mass-radius curve via TOV. The mass and radius define compactness, redshift, light bending, spin limits, tidal deformability. The star's rotation and magnetic field define magnetospheric structure and torque. Accretion, if present, defines boundary layers, thermonuclear ignition, and spin evolution. Crust physics defines glitch behavior and seismic modes. Superfluid and superconducting phases define coupling and magnetic evolution. Each observable is therefore a projection of interior physics onto signals in space. The monster breaks rules because it forces a scientist to carry the chain of reasoning without skipping any link. It is not permissible to treat it as a simple sphere of neutrons if one seeks to explain glitches, nor as a perfect dipole if one seeks to explain burst phenomenology, nor as a Newtonian object if one seeks to model pulse profiles or gravitational wave signatures. At still greater depth, consider causality and the speed of sound in dense matter. The stiffness of the equation of state is related to the derivative dp/d epsilon, where p is pressure and epsilon is energy density. The square of the sound speed is c underscore is superscript 2 equals dp/d epsilon in relativistic units. Causality requires c underscore less than or equal to c. Some theoretical models allow c underscore s to exceed c if used outside their valid regime. Such models must be rejected. The maximum mass of neutron stars can be increased by making the equation of state stiff at high density, but stiffness is limited by causality and by microphysical constraints. Observing a very massive neutron star forces the equation of state to be stiff enough, possibly implying strong repulsive interactions at high density or phase transitions that stiffen the matter. Conversely, if a phase transition to deconfined quark matter occurs, the equation of state may soften, potentially reducing maximum mass unless the quark matter itself becomes stiff through strong coupling. These possibilities create the concept of hybrid stars, neutron stars with quark cores. In such a case, the monster could be not a black hole, but might contain matter in a state otherwise unattainable, a bulk of deconfined quarks, perhaps in a color superconducting phase. The existence of such phases is not established with certainty, but the requirement here is not to speculate beyond the topic's scope. It is to remain within the principle that neutron star interiors probe extreme QCD regimes. The monster's behavior is therefore partly a message from the strong interaction under conditions of high baryon chemical potential. That is the most fundamental layer. The object is an astrophysical manifestation of quantum chromodynamics in a regime not easily accessible by terrestrial experiments. In the presence of such uncertainties, one might expect the story to become loose. Instead, the monster forces precision because any proposed interior must satisfy multiple constraints simultaneously, support observed masses, match observed radii and deformabilities, explain cooling behaviors, allow glitch reservoirs, and be consistent with nuclear physics. The object breaks rules because it refuses single explanation comfort. It demands a coherent physical model across domains. The monster's exterior, the crust and magnetosphere, can also produce phenomena that look like black hole behavior in certain observational bands. For instance, in X-ray binaries, quasi-periodic oscillations in the X-ray flux can occur at kilohertz frequencies. Some interpretations tie these to orbital motion near the inner disk edge. For a neutron star, the inner disk can approach close to the surface or be truncated by magnetosphere. The orbital frequencies at such radii can be kilohertz. The presence of twin kilohertz QPOs, their separation, their variation with accretion rate, and their relation to spin can inform models. In black hole systems, high-frequency QPOs also occur, but the presence of surface in neutron stars introduces boundary layer emission and potential beat frequency interactions. Again, the monster is not a black hole, because the same gravitational field scale yields similar frequencies, but the additional physical boundary conditions change the signal. The phrase cosmic monster also applies to the violence of compactness when interacting with normal matter. Consider tidal disruption. A neutron star approaching another object can tidally strip matter. In a neutron-star merger, tidal forces and shocks heat matter, leading to nucleosynthesis through rapid neutron capture, the R process, producing heavy elements. While the broader implications of heavy element creation can drift beyond the topic, the key remains within the monster's rule-breaking. Neutron star matter is so neutron-rich that when ejected and decompressing, it undergoes nuclear reactions that can create nuclei heavier than iron. This is an outcome of the neutron chemical potential and the initial composition. The merger ejecta also powers electromagnetic transients. Black hole neutron star mergers can also eject matter, depending on parameters. But neutron star mergers uniquely involve two surfaces and two reservoirs of neutron-rich matter. The existence of matter in that state is a neutron star specialty. It breaks the rule that heavy elements must be forged only in stellar interiors or supernovae. The neutron star provides a different environment, albeit in rare violent events. Even without mergers, isolated neutron stars can be monsters through their interactions with interstellar medium and their own remnants. A young neutron star can power a pulsar wind nebula, injecting relativistic particles and magnetic fields into surrounding space. The wind termination shock and synchrotron emission can create bright nebulae. The energy source is rotation. The spin-down luminosity can be immense for young pulsars. The object becomes an engine driving relativistic outflows. Black holes can drive jets too, but typically through accretion and magnetic extraction of rotational energy via processes like Blanford's Najek. Neutron star winds are different. They're driven by the rotating magnetosphere of a surface-bearing star. The monster breaks the rule that a compact object's influence is limited to gravity. Here, it is an electromagnetic rotator that can dominate a nebula's energy budget. Return again to the surface and the crust because the not a black hole distinction is anchored there. The crust's rigidity can store elastic energy. Starquakes can happen when spin-down reduces oblateness, and the crust resists adjustment, building stress until it cracks. This can cause sudden changes in moment of inertia and spin, potentially explaining glitches and bursts. In magnetars, crust fractures can be driven by magnetic stress rather than spin evolution. The fracture can couple to the magnetosphere and trigger reconnection. The timescales can be milliseconds, matching burst rise times. The energy scale can be large. The key is that this is solid-state physics in a relativistic gravitational field. The monster is a crystal lattice under extreme pressure, with shear modulus determined by Coulomb interactions among nuclei and electrons, and with defects and fractures that can propagate. The propagation of a crack in a neutron star crust involved conditions utterly unlike terrestrial materials. Gravity is enormous, the pressure is extreme, and the material is near neutron drip in some regions. Yet the notion of fracture remains meaningful because the crust behaves elastically until yield. This is a rule broken in the sense that star is not supposed to be a brittle object that cracks. At still deeper levels, consider the interplay of superconductivity and magnetic field evolution. If protons in the core are superconducting, The magnetic field is carried by quantized flux tubes. The movement of these flux tubes, their pinning to the lattice or interaction with vortices, affects how the field decays or evolves. Magnetic field decay timescales influence the life cycle of pulsars and magnetars. In a normal conductor, magnetic fields decay via ohmic dissipation. In a superconductor, dissipation is suppressed, but flux tube motion can still allow evolution. The crust may not be superconducting. It is a conductor with finite resistivity. Hall drift, a nonlinear process in magnetized electron fluids, can rearrange field structure in the crust. Hall drift can transfer energy to smaller scales where ohmic dissipation is more effective. This can heat the crust and contribute to magnetar emission. The monster's magnetism is thus not static. It is a dynamic interplay of superconducting and normal regions, of electron flows, of crustal impurities, of temperature-dependent resistivity. The field is both a structure and an evolving system. The concept of impurities matters. The electrical conductivity of the crust depends on scattering of electrons off phonons and impurities. At low temperatures, impurity scattering dominates. The impurity parameter, measuring charge dispersion among ions, affects conductivity and thus magnetic field decay. It also affects thermal conductivity. Therefore, microscopic composition distribution influences macroscopic field evolution and surface temperature patterns. The monster is therefore a place where nuclear reaction pathways in the crust, which determine composition, influence the star's observable behavior over thousands to millions of years. Accretion can change crust composition through accreted crust processes. As matter is buried by continued accretion, it is compressed and undergoes a sequence of electron captures, neutron emissions, and pycnonuclear reactions. These reactions release heat, called deep crustal heating, which can keep transiently accreting neutron stars warm. When accretion stops, the crust cools, and observations of cooling curves after outbursts can probe crust conductivity and heat capacity. Again, the monster's crust is a nuclear reactor driven by compression rather than temperature. Pycnonuclear fusion occurs when nuclei fuse due to quantum tunneling enhanced by high density, even at low temperature. This breaks the ordinary rule that fusion requires high temperature. In neutron star crusts, density can make fusion proceed through tunneling because nuclei are packed close together. The star thus hosts nuclear reactions in cold, dense matter. Another rule broken relative to familiar stellar fusion. Now return, again and again, to the central comparison, not a black hole. A black hole's defining feature is the horizon. A neutron star's defining feature is that it is compact enough to be relativistic but not compact enough to form a horizon, and it has matter in extreme states. Therefore, the monster's uniqueness comes from the combination of extreme gravity and extreme material physics. Black holes give extreme gravity without material surfaces. Ordinary stars give material physics without extreme gravity. Neutron stars, especially magnetars and massive pulsars, give both at once. That is the reason they break so many rules that were learned in less extreme contexts. The monster's gravitational field also affects how matter falls and spreads on the surface. Accreted material, guided by magnetic field lines, can form hotspots. The emission from hotspots is modulated by rotation. The pulse profile depends on hotspot shape, beaming pattern, and relativistic light bending. If the star rotates rapidly, special relativistic Doppler boosting and aberration modify the pulse, and gravitational time delays across the surface contribute. Modeling these effects can constrain radius and mass. The monster's spin and gravity therefore encode its size in light curves. The star becomes a geometric instrument. The same cannot be done for a black hole because there is no surface hotspot anchored to a rigid rotator in the same manner. The monster's surface can also support an ocean of liquid nuclei and electrons above the crust, depending on temperature and composition. In accreting systems, this ocean can undergo thermonuclear burning and convection. The burning front can propagate across the surface, producing burst oscillations that reflect spin. These burst oscillations can be used to infer spin frequency. The propagation depends on Coriolis forces, which are strong due to rapid rotation. The dynamics of flame spread on a neutron star surface involve hydrodynamics under extreme gravity and rotation. Again, a star behaves like a planet's atmosphere in some respects, but under conditions that are far from terrestrial. The monster breaks the rule that surface processes are minor compared to stellar interiors. Here, surface burning can dominate observable behavior. In magnetars, surface emission is also shaped by atmospheric physics and strong fields. Radiative transfer must include polarization-dependent opacities. Vacuum polarization introduces resonances. Photon splitting can occur in ultra-strong fields, where a single photon splits into two lower-energy photons, a QED process. This modifies high-energy spectra. The atmosphere may condense into a solid or liquid surface under strong fields, depending on temperature and field strength, forming a condensed metallic surface. In such cases, the boundary condition for radiation changes. The monster's surface can be a condensed matter system under a magnetic field so strong that it changes phase boundaries. It is neither a typical plasma atmosphere nor a typical solid. It is a magnetized, condensed surface with unique emissivity. This again breaks rules built from ordinary stellar atmospheres. A further aspect, the neutron star's mass distribution and rotation can cause relativistic precession in surrounding orbits. In binary systems, strong gravity can produce periastron advance, Shapiro delay, gravitational redshift, and orbital decay due to gravitational wave emission. Timing of pulsars and binaries has been a premier test of general relativity. The neutron star acts as a clock and a mass simultaneously. Its pulses provide precise time markers, allowing measurement of relativistic effects. The monster is therefore an object where strong field gravity can be tested without a black hole. Black hole binaries can also test relativity through gravitational waves, but pulsar timing provides a different channel. The neutron star's non-black hole nature is not a limitation. It is an asset because the pulses provide a direct measurement tool. At the far edge of the monster's rule-breaking is the possibility of metastability and collapse triggered by accretion or spin-down. A neutron star can be stabilized partly by rotation. Rapid rotation provides centrifugal support, allowing a higher maximum mass than for a non-rotating configuration. As a star spins down, it loses that support. A star that is supermassive, meaning stable only because of rotation, can eventually collapse to a black hole when it slows sufficiently. In such a scenario, the object is not a black hole until the moment it becomes one. The observational signature of such a collapse could be abrupt cessation of pulsations or emission, possibly accompanied by transient. Within the topic scope, the important concept is that neutron stars can inhabit a narrow parameter space near collapse, and their evolution can move them across the boundary. The monster is therefore a cliff-edge object, a stable remnant whose stability is conditional. Conditional stability also arises from phase transitions. If the core undergoes a phase transition, the equation of state may soften, reducing maximum mass and potentially causing collapse for stars above the new limit. Alternatively, a strong first-order phase transition could lead to a twin star scenario, where two stable configurations exist with same mass but different radii. Such structure would mean that as a star's central density changes, it could transition between branches, potentially releasing energy. Again, the topic remains neutron stars as rule-breaking monsters, not black holes. The essence is that internal microphysics can produce macroscopic bifurcations in structure, a feature absent in black holes. A black hole does not have phase transitions in matter because it has no matter configuration described externally. Another rule broken is the rule of transparency. Neutron star interiors are opaque to photons. Radiation cannot escape from deep inside, but neutrinos can. And in the earliest seconds after formation, neutrinos carry away most of the gravitational binding energy, around 10 to the power of 53 ergs. This is the energy released in core collapse supernovae. The neutrino burst from a nearby supernova would provide direct information about neutron star formation. The object is therefore an engine where the weak interaction dominates energy flow, unlike ordinary stars where photons dominate. The monster's energy budget is controlled by neutrinos at birth. The gravitational binding energy itself is enormous because of compactness. For a neutron star, the binding energy can be around 10 to 20% of its rest mass energy, meaning that if one could disperse the star to infinity, that energy would be required. In formation, that energy is released mostly as neutrinos. This breaks the rule that gravitational energy release is small compared to rest mass. Here, it is a significant fraction. Yet the monster, despite its extremes, can persist for billions of years. Millisecond pulsars are old, recycled, stable rotators. Their longevity implies that the structure is robust, that the crust and magnetosphere can settle into stable configurations. The rule broken here is that extreme objects must be transient. Neutron stars can be both extreme and long-lived. The object's existence also challenges the boundary between macroscopic and microscopic. The crust thickness is a kilometer or less, yet it influences spin irregularities observed across the galaxy. The superfluid vortices are microscopic features, yet their collective behavior influences macroscopic rotation. The magnetic flux tubes are quantum objects, yet they shape global field evolution. The vacuum polarization effects are quantum, yet they influence polarization of X-ray photons from distant stars. The monster makes quantum field theory observable at astronomical distances through polarization signatures, makes superfluidity observable through timing glitches, makes nuclear physics observable through mass radius constraints. It breaks the implicit rule that quantum effects remain in laboratories. Hold again to the comparison. A black hole will be the endpoint if the object were more massive or if pressure could not resist further collapse. The neutron star exists because matter is stiff enough. Therefore, every rule broken by the monster is also a proof of stiffness. A black hole is a region of space-time where collapse has passed the point of no return. A neutron star is a region where collapse has been halted by microphysics. The monster is the halted collapse. That is the central physical meaning. Gravity pushes towards singular behavior. Nuclear matter pushes back. The equilibrium is an ongoing confrontation. Every observable phenomenon is a side effect of that confrontation. As the narration continues, the voice stays observational, the logic layered, the same core concepts revisited with increasing precision. Density is revisited not as a number, but as an energy scale. At nuclear density, the Fermi energy of neutrons is tens of MeV. The chemical potentials are high. Beta equilibrium sets the proton fraction. Charge neutrality requires electrons. At high density, muons appear when the electron chemical potential exceeds the muon rest mass energy. These leptons affect neutrino processes. The proton fraction affects whether direct ERCA is allowed, which affects cooling. Cooling affects superfluid transition timing, which affects glitch behavior and neutrino emission from pair breaking. The superfluid gaps affect heat capacity. Heat capacity affects thermal evolution. Thermal evolution affects crust conductivity. Conductivity affects magnetic field decay. Magnetic field decay affects magnetar activity. Magnetar activity affects observed bursts. Observed bursts provide clues to field strength and crust properties. Thus, a single chain runs from Fermi energies to observed gamma-ray flares. This is how the monster breaks rules. It makes the universe's most abstract microphysics into the cause of its most dramatic macroscopic displays. Relativity is revisited not as time dilation exists, but as the necessity of consistent metric solutions. The TOV equations couple pressure and mass energy. The moment of inertia depends on mass distribution, which depends on equation of state. Frame dragging depends on angular momentum distribution. Observed spin frequencies and spin-down rates tie to magnetic torque, but the torque depends on magnetospheric plasma supply. Plasma supply depends on pair creation. which depends on field curvature and strength. Field strength depends on internal field evolution and superconducting properties. Those depend on temperature and composition. Composition depends on formation and accretion history. History depends on binary evolution. Yet even here, the topic remains locked because every step is about the neutron star's monstrous nature and its rule-breaking behavior as not a black hole. In the accretion context, revisit the Eddington argument with deeper precision. The Eddington luminosity is L_ed equals 4 pi GMC/kappa, where kappa is opacity. 4 Thomson scattering in fully ionized hydrogen, kappa 0.34 square centimeters per G. This yields about 1.3 times 10 to the power of 38 erg/s per solar mass. But in strong magnetic fields, the scattering cross-section depends on polarization and photon energy relative to cyclotron energy. The effective kappa can be reduced for certain modes, increasing L_ed. In addition, if emission is beamed or anisotropic, the isotropic equivalent luminosity can exceed L_ed even if local luminosity does not. Moreover, in accretion columns, radiation can escape through the sides, changing force balance. Thus, ultraluminous X-ray pulsars can exhibit apparent luminosities above 10 to the power of 39 erg/s, once thought to require black holes, yet pulsations reveal neutron stars. This is a direct instance of breaks every rule, and it's not a black hole. The rule broken is the inference rule. High luminosity implies black hole. The neutron star demonstrates that geometry and magnetic physics can allow a surface-bearing object to shine at such levels. Similarly, magnetar flares can have peak luminosities that dwarf Eddington by many orders of magnitude, but Eddington is derived for steady, spherical, electron scattering limited outflow in a weak field. A magnetar flare is transient, magnetically confined, and radiative transfer occurs in a strongly magnetized, pair-loaded environment. Radiation pressure does not drive matter away in the same way, because magnetic confinement can dominate. Therefore, the Eddington concept does not apply straightforwardly. The magnetar breaks the rule by stepping outside the regime in which the rule was derived. The monster's surface gravity is revisited in terms of escape velocity. For a neutron star, escape velocity can be around 0.5 c or more, depending on compactness. This affects atmospheres. Gravitational settling is rapid, so heavy elements sink quickly unless supported by radiative forces or ongoing accretion. Thus, the atmosphere composition can become pure hydrogen if accretion supplies it, because heavier elements sink below. But in strong magnetic fields, diffusion may be altered. The thinness of the atmosphere means that radiative transfer occurs in a small column depth, but with large pressure gradients. The scale height is small because G is huge. The radiative spectrum depends on magnetic field and composition, so observed thermal spectra can constrain these properties. Again, the monster's gravity makes atmospheres microscopically thin. Now revisit rotation, now in the context of spacetime. A rapidly rotating neutron star can be described by a stationary axisymmetric metric. Frame dragging means inertial frames rotate. The Lenz-Thirring effect can cause nodal precession of tilted accretion disks. In principle, observed QPOs could relate to such precession. The star's quadrupole moment, due to oblateness, affects orbital frequencies. For black holes, these effects are described by Kerr metric with multipole moments determined by mass and spin. For neutron stars, multipole moments depend on equation of state. Therefore, the orbital dynamics around a neutron star differ subtly from those around a black hole of same mass and spin. Observing these differences is challenging but conceptually important. The monster's external spacetime is not fully characterized by mass and spin alone. Matter distribution leaves an imprint. The monster's capacity to emit both electromagnetic radiation and gravitational radiation is also revisited. A rotating, magnetized star emits electromagnetic dipole radiation if magnetic axis is misaligned with rotation axis. The power is approximately 2/3 3c3, mu 2 omega 4 sin 2 alpha in vacuum dipole approximation, where mu is magnetic dipole moment. Real magnetospheres alter this coefficient, but the scaling remains. Strong fields and fast spin yield high spin-down power. The spin-down changes omega over time. Observed period derivatives give estimates of magnetic field strength under assumptions. Magnetars have large period derivatives, implying strong fields. Yet their emission is not rotation-powered, showing that the inferred dipole is not the whole story. Internal fields may be stronger. The monster thus breaks the rule that dipole inference from timing directly tells the whole magnetic story. In gravitational waves, the star can emit through time-varying quadrupole moments, as in deformations or R modes. R modes are rotational modes driven unstable by gravitational radiation reaction in some regimes. Viscosity can damp them. The instability window depends on temperature, rotation rate, and microphysical viscosities, which depend on superfluidity and composition. If R modes were active, they could limit spin rates. Observed spin distributions can therefore constrain viscosity and superfluid parameters. Again, microphysics tied to macroscopic rotation. The monster breaks rules by turning viscosity, usually a mundane fluid property, into a determinant of how fast a star can spin across the galaxy. At this point, the narration remains continuous and unbroken, but the response here is still bounded by message limits. To comply with the user's request to generate the longest possible now, the text continues until the platform truncates it. When it truncates, the continuation can proceed seamlessly from the last sentence in a subsequent message on request, but within this single response, the maximum length is reached as closely as possible. Return yet again to the core. The neutron star is a balance between gravity and degeneracy plus nuclear repulsion. The maximum mass is the line beyond which the balance fails. The star near that line is the closest analog to a black hole without becoming one. Such a star has the deepest potential well, the largest redshift, the strongest light bending, the highest central density, and the greatest sensitivity to equation of state details. It is the monster because it occupies a boundary region of physical law where small changes in internal composition could alter global structure. It is not a black hole because it has not crossed the horizon threshold. It remains a material object. It can have earthquakes. It can have superfluid vortices. It can have superconducting flux tubes. It can have nuclear pasta. It can have an atmosphere. It can radiate. It can pulse. In this boundary regime, general relativity also predicts that the star's binding energy and baryonic mass differ significantly from gravitational mass. The gravitational mass is what is measured by orbital dynamics. The baryonic mass is the sum of rest masses of constituent baryons. The difference is binding energy. For a very compact star, the binding energy fraction is larger. This matters for formation. How much mass must collapse to yield a certain gravitational mass? It also matters for mergers and ejecta energetics. The monster thus has an internal accounting where mass is not simply additive. Mass is energy including gravitational field energy. The idea of surface also implies the possibility of reflection and reprocessing. In accreting systems, hard X-rays from a corona can irradiate the surface, producing reflection features like iron lines and Compton humps. The line profiles are shaped by relativistic Doppler and gravitational redshift. Disk reflection modeling can constrain inner disk radius. For a neutron star, the disk can extend close to the star, but the boundary layer can also contribute. The presence of a surface complicates the spectrum. The monster thus breaks the rule of clean accretion signatures. In rotation-powered pulsars, the polar cap region can be heated by return currents, producing thermal X-ray emission. The polar cap size depends on magnetic geometry and open field line region, roughly set by the light cylinder. The heating depends on particle acceleration and gaps. Observing polar cap temperatures and areas can constrain magnetospheric models. Again, a surface matters. In magnetars, the surface can be heated by magnetic dissipation, producing persistent X-ray emission. The spectrum can be modified by resonant Compton scattering in the magnetosphere, where soft photons scatter off magnetospheric charges. The scattering cross-section is enhanced near cyclotron resonance. This can produce hardtails and magnetar spectra. The monster's magnetosphere is therefore not a passive environment, but an active scattering medium shaped by strong fields and charge populations. The rule breaking continues in the timing noise and spin irregularities. Pulsars exhibit timing noise, deviations from simple spin down. This may reflect magnetospheric state changes, torque variations, or internal coupling variations. Some pulsars show mode switching, where pulse profiles change and spin-down rate changes, implying global magnetospheric reconfiguration. The star can switch between metastable magnetospheric states. This is a rule broken relative to the idea of a steady, rotating dipole. It is a complex plasma system capable of state changes. The monster's gravitational field also affects the propagation of radio waves through its magnetosphere, a surrounding medium. Dispersion measures, Faraday rotation, and scattering can be influenced by plasma densities and magnetic fields. In some systems, eclipses occur when a companion's wind blocks pulses. The interplay of pulsar wind and companion outflow creates plasma structures. While binary interactions can broaden beyond the topic, here it remains tied to neutron stars as electromagnetic engines in compact form. The more precisely the monster is defined, the clearer it becomes that the phrase "breaks every rule" is a shorthand for the repeated need to revise intuition. But the narration remains within strict scientific reasoning. The rule of scale, density, rotation, magnetism, emission limits, matter phase behavior, quantum macroscopic effects, and strong field gravity all converge. The monster is the neutron star at its extremes, especially the magnetar and the ultraluminous accreting pulsar, the massive near-maximum object, the millisecond pulsar with quantum glitch behavior, the star whose vacuum becomes birefringent around it, whose crust hosts density-driven fusion, whose core hosts superfluidity and superconductivity, whose gravitational field bends light so strongly that a far-side hotspot can still be seen, whose surface redshifts photons measurably, whose interior equation of state is encoded in gravitational waves, whose magnetic stresses can fracture nuclear matter. The narration continues, deepening the revisits. Consider the sheer modulus of the crust. In a Coulomb crystal of ions with charge Z and number density n_i, the shear modulus mu is on the order of 0.1 n_i Z caret 2/a, whereas the ion sphere radius related to density. This is enormous compared to terrestrial materials, but it exists under enormous pressure. The breaking strain, for molecular dynamic simulations, may be around 0.1, indicating the crust can sustain significant stress. This supports the idea that neutron star crust can sustain mountains large enough to emit continuous gravitational waves if asymmetries exist. The mountain size is limited by gravity and crust strength. The gravitational wave amplitude depends on ellipticity. If ellipticity is around 10 to the power of -6 to 10 to the power of -5, signals might be detectable for nearby, fast rotators. The monster thus could be a continuous gravitational wave source. A black hole cannot sustain a mountain. It has no crust. Now, consider the core viscosity. Bulk viscosity arises from deviation from beta equilibrium during oscillations, causing weak interactions to restore equilibrium and dissipate energy. Shear viscosity arises from particle scattering. Superfluidity suppresses some processes. If exotic particles like hyperons exist, they can increase bulk viscosity. Quark matter can have different viscosities. These viscosities determine damping of R modes and other oscillations. Thus, observed spin rates constrain viscosities and therefore composition. Again, interior microphysics influences global behavior. Consider the moment of inertia. For a neutron star, I is roughly 0.35 to 0.4. mr2, depending on compactness and equation of state. Precise measurement of moment of inertia in a binary pulsar could constrain radius and equation of state. The monster's rotational dynamics thus becomes a probe. Consider the gravitational field at the surface in terms of compactness and curvature. The Kretschmann scalar, a measure of space-time curvature for a Schwarzschild metric, is proportional to gem(2) to the power of 4 or to the power of 6. At the surface of a neutron star, this curvature is huge compared to Earth's, though much less than at a black hole horizon of stellar mass because radius differs. Yet it is within reach of strong field tests. The monster's spacetime curvature is a parameter that can be compared to other environments. Consider the interplay of magnetic field and crustal composition further. Magnetic stresses can cause plastic flow rather than brittle fracture depending on temperature and strain rate. The crust may yield plastically, allowing gradual twist injection into magnetosphere, leading to persistent emission changes. Sudden fracture may produce bursts. The distinction between plastic and brittle behavior depends on microphysics. The monster thus includes rheology, the flow behavior of nuclear matter under stress, in a context where the stress is magnetic and the material is a Coulomb lattice near neutron drip. Consider pair creation in magnetospheres. In strong magnetic fields, photon splitting can suppress pair creation by reducing photon energies, potentially affecting radio emission. This is one proposed reason why magnetars are radio quiet, though some magnetars are radio loud. The details depend on field geometry and twist. The monster's emission properties thus depend on QED processes in strong fields. Consider the light cylinder and magnetospheric current systems. The open field line region supports currents that flow out and return, creating a global current circuit. The spin-down torque depends on how open field lines are and on plasma supply. State changes in magnetosphere can change torque, observable as changes in period derivative. The monster's spin evolution is therefore not purely internal. It is influenced by magnetospheric plasma, which can change. Consider accretion torque in ultraluminous pulsars. The magnetospheric radius depends on magnetic dipole moment and accretion rate, roughly where magnetic pressure balances ram pressure. If accretion rate is high, magnetosphere is pushed inward. The corotation radius is where Keplerian orbital frequency equals spin. If magnetosphere is inside corotation, accretion proceeds and spins up the star. If outside, propeller effect can eject matter. The equilibrium spin occurs near where magnetospheric radius equals corotation. Observed spin-up rates can constrain magnetic field and accretion rate. The monster's high luminosity and pulsations thus can constrain its field strength, which may be lower than magnetar fields but still strong. The monster's bursts in accreting systems include photospheric radius expansion bursts, where luminosity reaches Eddington and the photosphere expands, cooling and changing spectrum. The expansion provides a way to estimate Eddington luminosity and thus mass and radius, though uncertainties are significant. Still, the phenomenon again requires a surface.